Hi, in this video, I will be showing you problem number 17 of chapter 11 section 8. Find the radius of convergence and the interval of convergence of the series sigma n varying from 2 through infinity x plus 2 to the exponent n divided by 2 to the power n ln n. Anytime when the question is about radius of convergence, we will be using the ratio test for convergence. So what is ratio test? If limit is n approaching infinity, absolute an plus 1 over an is L, and if that L is less than 1, then the given series is absolutely convergent and hence convergent. Limit is n approaching infinity, absolute an plus 1 an equal to L, but L is more than 1, then the series is divergent. If this ratio is equal to 1 as n approaching infinity, then the test fails, or it is inconclusive. No conclusion can be drawn about the convergence or divergence of the series, in which case you have to apply a different test. Now we're going to consider this ratio. So let's consider an plus 1 over an, which is x plus 2 to the power n plus 1 over 2 to the power n plus 1, ln of n plus 1. Then I'm dividing by an is this x replaced by, we have to divide this by an. An is just this part. So we have to flip and multiply. So it is going to be 2 to the power n ln n on the numerator divided by x plus 2 to the power n at the denominator. We can simplify this algebraically. X plus 2 to the power n, x plus 2 to the power n plus 1. That will give us x plus 2. And 2 to the power n, 2 to the power n plus 1. That will give us 2 in the denominator. So we get x plus 2 over 2. Then ln n over ln of n plus 1. Now we'll apply the limit as n approaching infinity. Absolute of an plus 1 over an, which is just this expression with the absolute sign introduced. And then absolute of 2 is 2, so we don't put the absolute sign here. So absolute x plus 2 over 2, because we are only allowing n to approach infinity, the term involving n only will get affected. So absolute x plus 2 over 2 can be taken out of the limit. So limit is n approaching infinity, absolute ln n over ln of n plus 1. So if you directly plug in n, it becomes ln of infinity over ln of infinity, which is kind of indeterminate. Therefore, we have to apply L'Hopital rule for the relating function. So let's consider the relating function for this one. So we are going to consider ln x over ln of x plus 1, and then we are going to allow x to approach infinity. So as it is, it's infinity over infinity, which is indeterminate quotient. So we're going to apply the L'Hopital rule, which is the derivative of the numerator over derivative of denominator, which is derivative of numerator is 1 over x, derivative of denominator is 1 over x plus 1. So it becomes limit as x approaching infinity, x plus 1 over x, which in turn can be written as limit is x approaching infinity, 1 plus 1 over x. X over x is 1, 1 over x. Inside we are going to do like that. As x approaching infinity, 1 over x will approach 0. So it is simply 1. So this part from the step that we have proved becomes 1. So limit n approaching infinity, absolute an plus 1 over an is absolute x plus 2 over 2. The other limit part that we just now showed equal to 1. From what we have proved here. So it's equal to 1. So from the ratio test though, we have here absolute an plus 1 over an is equal to L, and if L is less than 1, that will establish the absolute convergence. So according to that ratio test, absolute x plus 2 over 2 less than 1 would mean it's absolute convergence. So absolute x plus 2 should be less than 2 in order for convergence. So we'll have the radius of convergence would mean, so this would mean the series is convergent. So this shows that radius of convergence equal to this number 2. So radius of convergence equal to 2. Now we have to find out the interval of convergence. The next part is to do the interval of convergence. The first part says is absolute x plus 2 less than 2 would mean x plus 2 lies between negative 2 and positive 2. Or in other words, if you subtract 2 on all sides, it will be x less than 0, and then here it will be greater than negative 4. So the interval of convergence could be negative 4 to 0, both inclusive, or one of them inclusive, but not the other. So we are going to check the endpoints. At endpoints, namely between negative 4 and 0, it definitely converges. What question remains is what happens at negative 4 and what happens at 0. So we will substitute at this point x equal to negative 4. So substitute x equal to negative 4 into the original series. So the given series is sigma n varying from 2 through infinity x plus 2 to the exponent n divided by 2 to the power n, then ln n. And in this we are going to substitute x equal to negative 4. So negative 4 plus 2 to the power n over 2 to the power n ln n. This would be sigma negative 2 to the power n over 2 to the power n ln n varying from 2 through infinity, which can once again be written as 2 through infinity sigma negative 1 to the power n 2 to the power n divided by 2 to the power n ln of n. So this 2 to the power n can be crossed out. So we get the series now to be n varying from 2 through infinity negative 1 to the power n divided by ln of n. So this is an alternating series. In order to see whether the series converges at negative 4, we have to see whether this alternating series is convergent or not. So we are going to test by alternating series test. So there are two requirements for the alternating series. So bn plus 1 should be less than or equal to bn for n. Then number 2 would be limit as n approaching infinity of bn equal to 0. These two conditions must be satisfied. So clearly ln of n plus 1 is less than ln n, greater than ln n. The 1 over ln of n plus 1 would be less than 1 over ln n. That proves bn plus 1 is less than or equal to bn for all n more than 1. But anyway, the series starts only from 2. We can say for more than or equal to 2. And then the second condition, limit as n approaching infinity of Bn, is limit as n approaching infinity of 1 over ln n. So Bn is this series without this alternating series without the sign. So it's limit as n approaching infinity 1 over ln n. So n approaches infinity, therefore ln n would also approach infinity. So it's 1 over a large number, that is 0. So we have proved both conditions, condition 1 and then condition 2, that limit of Bn equal to 0. Together it shows by alternating series test the series is convergent. So by alternating series test, we can say sigma n varying from 2 through infinity negative 1 to the power n over ln of n is convergent, which pretty much proves that one endpoint, namely x equal to negative 4, the series is convergent. So now we have to check what happens at the other endpoint, namely 0. What happens at 0? So let's plug in x equal to 0. So substitute x equal to 0 into the function here. So the series becomes sigma n varying from 2 through infinity x plus 2 to the power n over 2 to the power n ln n would become sigma n varying from 2 through infinity 0 plus 2 to the power n. So 2 to the power n over 2 to the power n ln n. Here it is simply sigma 1 over ln n. So we are going to show that this one is divergent. So we are going to use here the comparison test. So let's take an to be equal to 1 over ln n and then bn to be equal to 1 over n. So we have a relation that ln n, the logarithm of any number is less than the number. So 1 over ln of n will be more than 1 over n. So if we consider sigma of 1 over n or sigma of bn, which would be sigma of 1 over n, which is a p series or harmonic series, which is with p equal to 1, so which is divergent, as we have an which is more than bn and sigma bn diverges, by comparison test we can conclude sigma an, which is nothing but sigma 1 over ln n, also diverges. What we have proved just now is at this point x equal to 0, the series is divergent. At the endpoint negative 4, which we proved initially, the series is convergent by alternating series test. So looking at all this, we have concluded that radius of convergence and from part A is equal to 2, and the interval of convergence at negative 4 it converges, but at 0 it doesn't converge. But we already know from negative 4 through 0 the series converges. So interval of convergence is close to negative 4, open 0 in that interval. and the radius of convergence is 2.